Welcome to Breadboarding. This is video 8 in the Breadboard 8088 PC series, and in this video we'll be continuing the testing of the EEPROM and the RAM that we installed in the previous video, and we'll be doing some 8086 assembler. So if you haven't seen the previous video where we installed the EEPROM and the RAM and the address decoder, then there'll be a link on the top right here that'll take you back to that video. Suggest you watch that video first before this one, as it won't make too much sense without it. And in this video what we're going to do is write a test program in Intel 8086 assembler. We'll then burn that to EEPROM in the appropriate location so that the code gets run when the processor resets, and then that program will then be writing to, then reading from the RAM. So this will allow us to check to see that we can run code in the sort of reset vector for the processor, and also that we can access the RAM. I don't have much experience of 8086 assembly language, so apologies if there's anything obvious that I'm saying or any mistakes I'm making here. I've got quite a bit of experience of using the 6809 assembly language and some Z80, but I've never done much on the 8086 side of things. To help with this, I've made use of Slader's toolchain setup for 16-bit Intel 8088 step by step. So that YouTube video I strongly recommend you have a look at if you want to do this. In addition to the video, there's links for all the tools and things. So NASM is the assembler that we'll be using for this, and in future videos we'll also need to use some of the C environment as well. So follow this one. There was a comment I did ask, the source code that's referenced from here has moved location slightly. You may want to have a look if you're looking at this. The source code is now under the eco as an IO device for the BIOS. And I've also made use of the XI8088 Sergey's XT BIOS, the reset handling and the specifics of how to set the memory up in the assembler to ensure that when you burn this to ROM that it will execute in the right code segment and everything. I've used references to Sergey's 8088 there. The URL is there. You can see here from the README and the make file. So the NASM command line, for example, that is used to build the BIOS. So the 8086 is a 16-bit processor, but is able to access 1 megabyte or a 20-bit address range. Now, the way how Intel did this was by a segmented memory model. And what this basically means is that in addition to the normal 16-bit registers you might be familiar with, there's an additional set of 4 registers known as the segment registers. So there's a code segment for the executable code, data segment generally for the primary accessing the data, stack for manipulating the stack, and the extra segment is normally used for extra data. Now, the TestRAM program is using the data segment register, so the addresses are going to be based on the data segment and the data index register DI. And the way how this works is that the physical 20-bit memory address is made up of the segment register shifted 4 bits left or multiplied by 16, whichever way you want to think about it, added to the other register value. So we end up with a 20-bit memory address. The way how these two can be added together means that they're actually, for the same physical address, there could be lots of different ways of producing that using the segment and the base index register. Now, the reset address is FFFF0, so that's really 1 megabyte minus 16. And on reset, the code segment register is set to 4 Fs and the instruction pointer is set to 0. So that means you get the FFFF0 there. And this is normally represented the segment first and then the logical address. In order to calculate the physical address, you'd have to take this, times it by 16, and then add it to that. So we're going to be using the DS and DI to access the RAM. There's one thing I did discover: you can't add, compare, test segment registers. So you have to copy the segment register to another register first before you can do anything like that. And there is a useful Intel IAPX 88 book. So IAPX was the name they gave to the overall 8086, 8088 architecture. And that book's quite useful, include more detailed information about all the instructions and also identifies what happens during reset. So let's take a look at the test program. So this is based on some of the information in Sergey Kislev's code. This is the command line to assemble it. And all this is doing is writing an 8-bit ascending byte to addresses from the base 0 up to 7 FFFF, which is the first 512k. This is telling the assembler it's using 8086 instructions, so it won't use any of the 386, 486 Pentium upwards instructions. The macro included here is one from Sergey, and all this does is pads code to a particular address. So if we want to actually fill out the previous chunk of code with FF so that we can get to another address, then that's useful for building the ROMs. So this is in fact starting at 8000, so the physical address is in fact going to be F8000 is where the ROM is actually located. So code actually starting at the beginning here will be at the bottom of the ROM. And what we should do is to have a look that the reset process is basically going to start at F0, but within this particular code, because we're only working with the 16-bit address here, this is actually location it will start at. And the first instruction we've got here is jump to F000 test start. So this should in fact be going to F8000. So that this aspect of it is really quite confusing, and having a working example already was a lot easier to work from rather than having to work this out for myself from scratch. So given that we've got the beginning of the code here will be jumped to from the reset jump instruction at the end there, what we're actually doing here is we're just initializing some registers. We're zeroing the data segment register. XORing DI, we're basically XORing something with itself, just clears it, zeros it. And then we have a loop here where we're just moving the lower byte for the BX register. So we're just taking the bottom 8 bits, and all we're doing is we're storing that to the data segment data index combination, and that data segment data index combination is going to iterate through the bottom 512k of RAM. So we increase the data value that we're using, and that will just overflow through 255 back to 0. We increment the DI index, and then if that hasn't overflowed to 0, then we just go around in the loop, and we keep on going around there until such time as we've done 64k of data. So when the DI overflows, goes back to 0, what we have to do is to add 1000 to the data segment directly. So that effectively says use the next 64k segment. Now, because we can't directly modify the data segment, we can't do adds and compares on the data segment. So we have to move it into the AX register first, then we can add our 1000 to it. So that basically adds another 64k block to it, and then we move it back again. Then finally, we compare the value that we got there, and when we've done 0 to 7000, so that's the first 8 blocks of 64k, then we'll have got into the upper 512k of memory, and so for the moment we'll stop. If we add some more memory, we might need to change this. So then it jumps back to fill memory. Once it's done 512k, it then goes into the read section. And the read section is very similar. We initialize the registers in much the same way. We're just reading the value. We're not doing anything with it. We increment the index register, keep on reading until such time as this overflows to 0. If it overflows back to 0, then we add 1000 to the data segment again to do the next 64k block. We repeat until we've done the first 8 64k segments. Once we finish that, all we do is go back and start all over again. So it'll just keep on reading in a continuous loop until such time as we reset the code. So it's a very simple test program. What it should allow us to do is to check to see that the ROM is working properly and that we're also able to store and read data from the RAM. Okay, so now we just need to assemble this test program and burn it into the EEPROM. So the command line for assembling this is here, so we're just going to do that. We'll just check the output files file here. So you can see at the end here there is a jump instruction with the address here. The addresses shown here at the moment aren't the physical addresses that go in the output code. We can then look at the top here, and in fact what we see here is that the first 6 bytes we have here will B8 0000 and BB 0000. So we need to look for that when we have jumped from EA 00F0 8000. So let's just have a look at the output that's produced. So this is in the hex viewer mode of Notepad++. So if you look at the end, so at 7FF0, and remember here, because the memory address for this is in fact F800, so we have to add that onto this, and so this means that this would be FFFF0, and we actually have EA 8000 F000. Now Intel is little endian rather than big endian, so big endian means this would be 8000 F000, which is the way how the Motorola world works. And I must admit my brain works in big endian mode, not really in little endian, but you know, it's just one of the things to get used to here. So what this indicates is that the place where it should be jumping to will be F000 in the code segment and 8000 in the instruction pointer. What this indicates is that this should be jumping to F000 in the code segment and 8000 in the instruction pointer. So if we go to the top, you can then see that we've got B8 0000 BB 0000. So that looks like that's the code that we were expecting. Okay, so we just need to now burn this into ROM. So I'm just going to take the EEPROM out of its zero insertion force socket. Make sure we get this into the right pins. Run XG Pro. And again, as I said with the PLDs, what I would recommend is once you've set the IC type here, I'd recommend trying to read the chip. Just from the point of view, if it can't read it, you might have put it in the wrong way. If you try and program the EEPROM when it's not plugged in properly, then you might damage it. We'll just erase this first. Okay, that's erased. If we reread it, we'll see it's all FF. Okay, so we just now need to load the bin file that we produced. So I've just done that. Yep. And we'll program that. Okay, so that's done. So now we can take that out and put it back in the board. Okay, so we'll now unplug the EEPROM programmer and we'll plug in the logic analyzer. The logic analyzer is the 32 channel one I have. So we've got the logic analyzer software here, and we're recording 20 million samples at 10 megahertz. So this is going to take a sample of about 20 seconds, and it's going to take probably about 40 seconds or so for it to take the samples, then read it all. And what we've got here is the address lines A0 to A19, so that's the 20 address lines. We've got the ROM chip enable, we've got memory read, memory write, so those are both active low, the reset, and we're waiting for the triggering on this to go from reset going from high to low, and then we've got the data lines as well. And we're looking here with the analyzers with the two lots of address line signals and D0 to D7. Okay, so I'm just going to turn on the bench power supply, and if we just run this, this will be waiting for the reset line to go from high to low. So that took about 40 seconds to load in total. So we can see here that in fact the memory write, we've got activity for it for the first 5 seconds or so, then after that just looks like we've gone into our read mode, so that looks like something's happening there. And we can see at the front beginning here where the reset is going from high to low. If we just zoom down to here, we'll see what's going on. So after reset, there's normally about 5 or 6, 7 cycles before the processor actually comes out of reset. And what we can see here is we've got the lower 16 address lines there, which are FFF0. The top 4 bits are F, so that is our reset vector, the reset location that we expect. And if we look down here, we can even see that the first byte that it's reading is EA. And if we go back to our output here, we can see that the first byte we expect is EA, and then we have our 80F0, as we saw down the bottom here. We see that EA 008000F0. So if we see that, then we know that that aspect is working. So at F1, F2, we've got 008000F0. Then after that, we would probably then expect that the memory address is then going to move to F800. So again, that's what we expect. So the code segment's still at F, but the top 4 address lines are still at F, but then we are starting at 8000. And if we go back to our assembly listing, that's where we expect to have our B8 and BB, then ATD8. There we go, we've got BB 000. Now you see this is about twice as wide, so it means there's 2 00s here, because you can see we've got 2 reads here, and each of those is 00. The logic analyzer only shows where there's a change in the values. Then we've got BB 00, then ATD8. So if we go back to here, ATD8. So it looks like the code has gone to the top reset area and then successfully come down here. Then as this starts to execute, what we're going to be looking for is where we've got writes going on to the memory. So the only thing that should be writing to the memory is our test code. So to start with, we're going to should be writing 0. So we've got 0 going to 00000 there. And then if we go a bit further along, then this is 1, 1. If we go a fair bit further along, so if we look at this one, so we've got 000F, 00 is the top 4 address lines, and 0F. So it looks like it's going through there. Then finally, where we saw where it went from writing the memory to reading it, we can just zoom into here now and just check to see that somewhere along here we should be going back to a memory address close to 0. There we go. So we've got memory address 0, 0, 0, 0, and then the upper 4 bits are also 0, and we're reading a value of 0. When we go to the next one, 0, 1 is reading 0, 1. If we scroll a fair old way along here and find there, so 0E, 0E. So it looks like it's reading back the same value. So I think we can be fairly sure that the code running in ROM is running okay, and it's also accessing the RAM. Okay, so we've now completed the EEPROM, the RAM, the address decoder, and made sure that we can write assembly language and to run that. In the next video, what I'm going to be doing is looking at adding a 7-segment LED display and keypad, very similar to the one done on the Nanocomp 6809 project. So this will mean adding a peripheral interface adapter and wiring up the LED display and keypad, and writing a bit of simple C code to at least test that. And then in later videos, we'll then port the whole Nanocomp 6809 assembly language monitor into C to see if we can use the Nanocomp C monitor for managing our 8088 computer. So if you don't want to miss out on future videos, please hit subscribe, and if you found the content useful, please hit like. It just helps to make the videos available to a wider number of people. Thanks for watching.